Good morning, everyone. Thanks for making it out this month's webinar with Well Data Labs. I'm Anthony. I'm from the Society of Petroleum Engineers Permian Basin Data Lake Study Group, and I'm going to kick it off quickly. So Sam Oda from Well Data Labs has enough time to cover his content. Looks like he has some good stuff put together for us, and we're going to hold the questions to the end so he can go through his content. But raise your hand or submit a question through the GoToWebinar dashboard or tool, I guess you can call it, and then we'll address those towards the end. And you'll get the recording and then later this week from us, so you guys can review anything you missed. Thanks, and I'll hand it off to Sam.
Hi, everyone. Can you hear me? Anthony, if you could let me know that my audio is working correctly, that'd be awesome.
Yes, sir. I can hear you. You're good. Good to go.
Perfect. Hi, everyone. Welcome to this webinar on modern data systems and analysis. First, I'd like to thank the SPE Permian Basin Data Analytics organizers for inviting me to speak to you today. So I purposely avoided using any buzzwords in the title because I imagine that many of you, like me, have heard people go on endlessly about deep learning and big data. Wait a sec, big data is so 2 years ago. Let's say AI and augmented intelligence. My guess is that you're probably tired of the hype or can't really tell what the jargon being thrown around means. I think that's really unfortunate because it prevents and slows down constructive conversation and gets in the way of identifying the right tools and techniques to solve your specific problems. I don't have an outline slide since this webinar is just 2 parts. The first part is about level setting and going over some down-to-earth definitions of popular terms, as well as some of the subtleties that don't get much attention, but are in fact pretty important. In the second part, I'll discuss a case study, which is about automatically extracting a hydraulic fracturing pump schedule, including the prop and step concentrations and durations from the time series data that's generated during a hydraulic fracturing job. So you might have guessed from my tone that I have a problem with jargon used in communication, especially among non-experts. It's not that jargon in and of itself is bad. In fact, it can be a really efficient way to speed up and be very precise in communication, as long as everyone knows the precise definition of the piece of jargon being used. Otherwise, it's an impediment to genuine communication. Lots of people use jargon to sound knowledgeable, and others just parrot what they've heard. Unfortunately, this leads to jargon taking on new meanings because everybody's using it and no one really knows what it means. So with that, let me start off with our first definition, which is just an algorithm. An algorithm is nothing more than a sequence of steps to follow to solve a task. It's essentially a recipe. Anybody can create an algorithm. Just list out a sequence of steps that someone needs to follow or a computer needs to follow to solve a problem. Now, if that's all there is to it, then why is a course in algorithm design usually considered by many computer science students at university to be one of the hardest courses they take? Well, of course, the catch is that designing an algorithm that's both correct and uses a reasonable amount of computational resources is in general more difficult than it might seem. Unlike people who might take liberty with your recipe instructions, the computer is going to execute exactly what you tell it to. Now, this is both good and bad. If you're precise and correct in your reasoning, then you don't have to worry about the computer making a mistake. On the other hand, if there is a problem, then it's all on you. For correctness, it usually comes down to using assumptions or making assumptions that you're unaware of making. For efficient resource usage, well, in a lot of cases, it's actually genuinely difficult to do well, and what people in algorithm design do research in. So let me try this analogy. People in algorithm design study the fundamental nature of information and computation in a way that's very similar to the role that physics plays in many science and engineering fields. Statistics. Why am I talking about statistics? Well, because I love reliable data-driven decision-making. Statistics is fundamental to analyzing data. However, most people were exposed to stats as a collection of recipes that you can follow to get a number like r squared. Now, these types of courses include rituals of manipulating sums of squares and least squares regression and other magical tables around null hypothesis testing. Unfortunately, the content of these courses were already fossils before you were born. And what's unfortunate is that I see a lot of machine learning and AI education following this template of applying recipes depending on some flowchart of situations. Modern stats isn't like that, and it hasn't been like this for decades. Statistics has been, since its beginning, a branch of applied mathematics which designs and analyzes methods for drawing reliable conclusions from imperfect data. Now, as I'm thinking about it, applied math doesn't even have quite the right connotation. Maybe I should say mathematical engineering. Now, just as a completions or reservoir engineer needs to be able to understand the fundamentals of things like stress and fluid flow to design equipment and procedures, statisticians need to understand the fundamentals of data generation, uncertainty, and information to design effective methods and procedures. Now, I'm going to claim, hopefully not controversially, that engineers have found physics models to be helpful in their jobs. Statisticians and even machine learners have found probabilistic models to be useful, and so probability is central to the study of statistics. I break up stats into three major areas. The first is the description and summarization of data. The second is predicting new data from old. And third is inference, or understanding how or why a system will change when you change its inputs or initial conditions. Some of you might wonder why I make the distinction between prediction and inference. And I'm going to return to this in a few slides. So one of my huge pet peeves with stats is that it has co-opted many day-to-day words and have turned them into jargon. So terms like average, bias, significance, and likelihood. Now, we use these terms all the time in day-to-day speech. Unfortunately, they have very specific and very narrow meanings in statistics. And so we see a lot of bad reporting and analysis because of this fact. And to be honest, some of the logic in classical statistics is just plain weird, even though it can be effective and has been the workhorse for a lot of analysis in the 20th century. Machine learning is actually closely related to stats. And a fairly standard definition is that it's the field of computer science that gives the ability of computers to learn without being explicitly programmed. If you're like me, you're like, what? Computers can learn? Again, the term learning is borrowed from everyday speech and has a much more narrow and technical definition, as I list on the slide. Once you peel back the layers, you realize how stupid a computer actually is. And it's not that I don't like the phrase without being explicitly programmed, because that's actually not quite true. In fact, the algorithm designer gives a machine learning algorithm a set of procedures or Lego blocks to use. Then the algorithm designer programs valid rules for connecting those Lego blocks based on how the algorithm is fitting the data. You, as the modeler, give the training algorithm a formula for quantifying what a mistake is and maybe how bad the mistake is. Machine learning algorithms build formulas to predict new data based on input. I think people forget this because with a modern machine learning model, you don't represent the model using a formula of the type you were tortured with in school. That is, you rarely see machine learning models expressed in the form of x squared plus y cubed plus x times y, etc. Machine learning models, formulas, might look weird because they might be representative as a set of trees or weights in a neural network. But in principle, it's still a rule that takes some input and spits out an output. Most machine learning algorithms work like this at a high level. They start with a guess for a formula, sometimes without even having looked at the data. The learning algorithm or the training algorithm evaluates how good its current guess or model does on some labeled training data. Then the training algorithm might be able to identify some things to improve its current possibly horrible guess. Then the training algorithm will tweak its guess and repeat this procedure. Now, it's because computers can execute these mechanical steps ridiculously fast that we are where we are today. Another thing is, I like to think of model training simply as calibrating parameters or weights based on data, and not quote unquote learning the parameters. Learning tends to imply more than what's really happening behind the scenes. Personally, I like using the word calibrating because I feel it's more honest than using the word learning. But I'll continue to use learning for the rest of the talk because that's the accepted nomenclature. Now, as promised, I'll discuss the difference between prediction and inference. How many of you are familiar with the Ptolemic or geocentric model of the universe? In this model, the Earth was the center of the universe and every other celestial object revolved around it. This was one of the most widely accepted scientific models in the West up until the Renaissance. Now, before you laugh it off as completely ridiculous and simple-minded, you should know that it was surprisingly accurate at predictions. And it was able to actually predict the locations of the stars reliably well. It's one of the things, astronomy and astrology were very tightly linked back in those days. And so getting the planets of the positions well was important. Now, given that the apparent motion of the planets and stars in the sky was almost periodic, or is almost periodic, can you guess what their method was effectively doing? There's a hint on the right-hand part of the slide. They were essentially computing a truncated Fourier series decomposition of the motion. Those ancients weren't so stupid, huh? My point is, while they could predict very well, most inferences that involved extrapolating behavior was fundamentally flawed. A lot of machine learning that I've seen, unfortunately, falls into this category. And I would argue it isn't surprising given that machine learning is focused primarily on prediction. The real consequences aren't felt until decision makers are making decisions, not fully appreciating the limits or the assumptions of the AI or ML models that they're using. There are now some of you might argue that there are modern ways to look inside black box machine learning models, things such as partial dependency plots and Shapley values. Now, I love these methods and they're wonderful methods, but they do not really address the problem and can be very misleading as they give you the illusion of understanding or causality, even in big data regimes. Stats and ML are working in the realm of inverse problems. Now, some of you might be familiar with the notion of ill-posed problems. Roughly speaking, problems are ill-posed when there isn't a unique solution. In general, modeling the data generating process is an inverse problem that is ill-posed. You have to make assumptions. I mean, given that the model is ill-posed, why do you think that by using machine learning, you're magically going to fix this? You're not going to. When you're training an ML model, you are making assumptions even if you don't think you are. You'll get a false sense of security using a sophisticated model. You get to hide behind the sophistication, metaphorically sticking your head in the ground. This is the reason I prefer simple models in general for practical and applied work. I personally am more likely to understand the limits of simple things. Complicated things, well, I mean, they're complicated. Artificial intelligence. Unlike many people, I don't equate artificial intelligence just with deep learning. In fact, a more official definition is it's any system that perceives its environment and takes actions that maximize its chance of success at some goal. Again, there are everyday words in this definition that are highlighted in orange that give people the idea that these systems do more than they actually do in reality. AI is almost as old as computing itself. Ideas for artificial intelligence go back at least to Babbage and Lovelace in the 1800s, and more explicitly with the work of Turing in the early 20th century, machine learning is a subset of AI. In general, personally, I associate AI with any computational system that is capable of executing some task that involves analyzing its environment, think data, and executing an action, think generating an output, that depends on its analysis. AI is a tricky thing. There are lots of things that we take for granted: GPS, driving directions, auto flagging of spam email, etc., that we don't think of as artificial intelligence, but at one time, fairly recently, were very much cutting edge AI problems. The problem with the general perception of AI is that it's a moving target. In general, we consider something to be artificial intelligence if it has a science fiction feel to it, but any technology tends to lose its AI status once it becomes mainstream. Feature engineering. It's actually really important to both statistics and machine learning and automation in general, and it's not a term that's well known outside of the data science community. A feature is a characteristic that might help when solving a problem. Feature engineering is the process of using specific domain knowledge of the data to create features that make machine learning algorithms work. I like this quote by Andrew Ng, who is a prominent machine learning and AI researcher at Stanford, had a prominent role at Google, and is now an executive at Baidu. He said that coming up with features is difficult, time-consuming, and requires expert knowledge. In fact, he goes on to say that applied machine learning is basically feature engineering. Now, I'm going to bring it down to earth a little bit. Calculations such as material balance time and G-function time are actually examples of feature engineering. These are calculations that allow a person or a model to better identify trends or events of interest. Normally, we think of these engineering calculations for use by people, but there's no reason that you can't use them as input to a machine learning model. And I'm going to explain the importance of using good features by way of an analogy. Here I have an example of a decision tree model. It's fairly accurate to think of the complexity of the model as a measure of the number of nodes in the decision tree. So you'll see one on the left that looks really complicated and another model on the right that looks fairly simple. So here goes the analogy. Imagine that you ask someone or a company to solve or automate a problem for you. Now, if you give them the necessary data, but it requires all sorts of unit conversions and it's spread across multiple tabs, the column headers are vague and confusing. Now imagine that they're not subject matter experts in your business, but you give them lots of examples of what you're looking for. Then yes, in principle, they could come up with a method to solve your problem. But I almost guarantee that it'll be needlessly complicated. Now contrast this with instead giving them the minimal amount of data. And by that I mean no extra data, but all the relevant data. Now you give them consistent units and you're precise and informative with your column headers. Again, they're not subject matter experts, but you give them lots of examples of what you're looking for. I again almost guarantee you that what they come up with will make a lot more sense and be much more on point, and moreover, be a ton simpler than the previous case. This is why good feature engineering is really important. It controls model complexity as well as model reality. So on to a data scientist. What is a data scientist? So there are a few official definitions floating around, and I'm not really happy with any of them. And I've been doing this for a really long time now, so I'm just going to give you my definition. A data scientist is simply an analyst with a modern skill set. Now, my colleagues in data science hate when I say this. Honestly, I feel like it makes them, I think they feel a little bit less special. Well, they shouldn't. Being a good data scientist is difficult. It's because of the modern skill set part. The modern skill set is a rapidly evolving and moving target. It takes a lot of effort to stay on top of all the technological advances and all the analytical techniques. But at the end of the day, a data scientist is analyzing data to help people make better decisions. As I mentioned before, the title of data scientist is relatively new. I would argue probably around 10 years old, at least when it became common. And when people first started using the term data scientist, it was very broad. Finding good people for these original roles was really hard because honestly of the breadth and depth of skills required. This is now fragmented into many different roles. Roles such as data and business analysts, machine learning and AI engineers, data engineers, and ML and AI researchers. In the interest of time, I'm not going to expand on this, but we can return to my take on the difference and the importance of each one of these roles at the end if people are interested. And with this, I'll stop with the definitions and move on to the practical application of these ideas to something in oil and gas. So let's move on to the case study. Now, since the case study is on hydraulic fracturing time series data, I'm going to do a quick overview to make sure that everybody's on the same page. Here is an example of a time series plot for a hydraulic fracturing treatment. The data is generated from various sensors attached to equipment, and it's collected in its raw form by software in the Frac van. Various auxiliary time series data can be added to the raw data. We refer to a specific measured stream of data as a data channel. 4 common channels to view in a treatment plot include the treating pressure, the slurry rate, the clean volume or slurry volume, and the proppant concentration. Now, these measurements can be either at surface or bottom hole. In actuality, at the end of the day, there can be hundreds of channels depending on what the service company and the operator agree to collect. It is common for several channels to be superimposed on a single plot with multiple y-axes to infer channel interrelationships that can be associated to times and events of interest. One common type of data enrichment is identifying various events, such as the start and end of a stage, when breakdown or ISIP, or when the ball seeps, or even when a diverting agent is used. Engineers can spend hours identifying and labeling these events for a job. I know this seems like it should be easy and fast, but in reality, it takes a deceivingly long amount of time to do this, and even longer to do it well. Manually selecting and labeling these events is tedious. This often leads to fatigue and an increased level of inaccuracy and inconsistency in the labels. Now, besides being tedious, there may not be established rules for a team or a larger organization to ensure that these events are identified using the same techniques. This is like that often, like you'll hear it, that every engineer has their own favorite method of picking. What is the real problem with inconsistent or inaccurate labeling? Garbage in, garbage out. This is an extremely well-known phrase in data analysis and broader than that, and yet it is often ignored or played down because honestly of the amount of time it takes to QC the data well. My favorite excuse is the data is good enough. In previous jobs, I've found opportunities to completely reverse people's understanding of the data and subsequent decisions that were made mainly based on taking the time to carefully check the data and correct it. In this slide, we're looking at average treating pressure, which are calculated based on the treating pressures between the start and end of each stage. We often see stages that include pressure tests at the beginning and most of the fall off and sometimes even beyond. Average treating rates and pressures can be completely distorted if some stages include this data and others don't. Also, depending on the questions you're trying to answer based on these summary statistics, you can either end up with low quality predictions, if not actually conclusions that are misleading. So in essence, what I'm trying to say is that consistent and accurate labeling is better. Hopefully this isn't controversial. I mean, even to be pedantic, this is true provided that you're asking the right questions in the first place and looking at the data correctly. Now here's a cartoon that describes our data training process. This is actually surprisingly difficult to do well in practice, even though it's been described in countless numbers of articles, books, and blog posts. So this is fundamentally an iterative process. After collecting the data and cleaning it, we start model training. Any model hyperparameters and thresholds should be identified using some form of cross-validation. Some of you might not be familiar with the term hyperparameter. Roughly speaking, a hyperparameter is a knob or a knob that you can use to tune how a model learns. In contrast with the parameters that you're trying to learn by the modeling process itself. Now, you cannot, maybe I should say you should not evaluate your model performance using the training data, since the performance will be biased to be better than it actually is. Now, this is kind of weird for some of you. If you're familiar with the concept of overfitting, then this is one manifestation of it. Roughly speaking, overfitting is fitting noise instead of signal in order to get a better measure of predictive performance. Now, I'm not saying this is malicious. This is just how machine learning algorithms work. The point of a test set is to give you a final, unbiased measure of your entire model building process. This includes all the modeling decisions in your training procedure, including any pre-processing, any algorithm selection, any feature or engineering or feature selection, and any hyperparameter tuning. All of these choices, when repeated, can lead to overfitting. Also, because the above modeling procedure can get really complicated, there is a possibility of leaking data, and this causes the chances of overfitting to become really high. Now, some of you, again, might not be familiar with the term data leakage. Data leakage is the creation of unexpected, additional information in the training data that allows the model to make unrealistically good assumptions. Some types of data leakage include leaking the test data or using the test data during training, or leaking the correct prediction or ground truth into the test data. Or, this is a really common one, leaking of information from the future into the past. I see this all the time in time series forecasting models. Now, I don't have enough time to go into any more depth on this, but if you're interested, you can look up, there are several good articles that you can Google for on data leakage, as well as nested cross-validation. Now, this is one of the reasons I think it's good for people interested in data analytics to do at least one Kaggle competition, one competitive Kaggle competition. In order to place well, you really have to understand data leakage and cross-validation. So enough, let's get on to what I promised you, the applied part of the work. So here's a pumping schedule. Evaluating past frac designs is really important. It helps one understand completion performance by highlighting and summarizing relevant engineering decisions. For example, in order to simulate fracture growth, your frac model needs a pumping schedule as input. What I'm going to describe is an automated procedure that uses just a few simple ideas to identify the different steps of a pumping schedule and generate several pertinent statistics based on the time series data that's collected in the field. Essentially, the process I'm going to describe returns an actual, or quote unquote as pumped, fracture treatment schedule, which you can use to compare to the designed one. There are several key operations to describe when designing a hydraulic frac treatment. The first step is pumping clean fluid, called a pad, to generate the fracture and control fluid loss. This is followed by pumping the slurry, which is a combination of the clean fluid and the proppant, in order to transport and place the proppant. The last step is a second iteration of pumping clean fluid called a flush to displace any slurry in the tubulars. Other optional steps may include 1, pumping a pre-pad, 2, using acid to clean the perforations, 3, or pumping a diverter agent, which can either be chemical or mechanical. Our team tends to use a lean-inspired methodology of breaking down problems into multiple simple subproblems and quickly iterating or failing on those subproblems. If we have time at the end, I have a detailed slide describing our team's process. For this project, we developed 4 models to annotate the data and describe the entire schedule. The first model identifies the stage start and end times and was actually developed by my colleagues Alberto Ramirez and Jessica Iriarte, I believe either last year or the year before. The second model identifies the proppant-related flags, like when the acid is pumped and when the proppant ramps start and end. The third model will in turn divide each proppant ramp into its constituent steps using piecewise constant regression. The fourth model you can think of as a post-processing step that takes the complementary time interval, and by that I mean the times between flags, and associates them with clean fluid areas such as the pads, sweeps, and flush. These models all compute various statistics such as volumes, durations, and averages for each of one of these intervals. There are several important data pre-processing steps that are required to prepare the data for analysis. Because we're using signal processing routines, it is crucial to ensure that the data is in chronological order, rows with the same timestamp are deduplicated, and that any missing data are handled appropriately. Now, our cloud-based platform handles the data duplication, the data loading, and ensures that the data is in chronological order. There are many choices for dealing with missing values. And in this simple case I'm going to describe, the model simply ignores them. We did explore another option of replacing the missing data with the most recent value that we actually had. And we tried both methods, and they both yielded similar test results on the validation data. So we went with the simpler thing. Now, the presence of negative values in the proppant concentration channel is one of the most common data anomalies we see. Now, this can be due to sensor miscalibration or the use of low-quality sensors. The pre-processing procedure simply replaces a negative value with 0. Clipping is called clipping. Another data anomaly related to sensor quality is when the proppant concentration is greater than 0 for the entire stage, even when the slurry rate is 0. So this is a recalibration step. The procedure simply shifts the entire proppant concentration channel so that the minimum value of the channel is 0. All this pre-processed data is used for identifying events. Any relevant statistics can be calculated using the original data. And remember, these are all modeling choices. You've got to be aware of overfitting and data leakage. At Well Data Labs, we use a lot of signal processing filters in our models as part of our feature engineering. Now, why signal processing? Well, one, we use time series data. Another reason has to do with the super efficient computations involved. Since time series data is typically stored in contiguous blocks of memory, it is really well suited for numerical processing on modern CPUs. The procedures described below take advantage of optimized routines for signal and array processing that you can find in most modern signal processing libraries. Calculating moving averages is perhaps one of the best known examples of a signal processing filter. Filters are examples of function transforms. A transform takes a function as input or a signal as input and returns a function or a signal as output. The derivative, the integral, The Fourier and Laplace transforms are all examples of function transforms. Now, filter design is a huge area of study with a lot of theory to help you understand the effect of filters and how to choose between them. You don't need to be an expert in the theory. Some basic knowledge is helpful because there's not a one-size-fits-all filter for every application. Filters, like most tools, come with trade-offs. A common use of filters is for smoothing data. There is an interesting and often underappreciated trade-off that affects most procedures that smooth data. Smoothing methods tend to considerably reduce noise in the smoother or flatter regions of the signal, but this comes at the expense of smearing out edges. And by an edge, I mean a sharp and potentially meaningful change in the signal. So for this application, the goal is to reduce noise in the signal while preserving edges as much as possible. If you look at the diagram on the right, it's going to illustrate what I'm going to talk about. In general, the moving or rolling median filter is better at removing noise while preserving edges for a given window size than a moving average. So if you look at this diagram, the moving median filter actually coincides with the edge in terms of time. Whereas if you look at the signal where it says edge degraded with simple smoothing, you'll see that the slope has flattened out. And this is really common when using a moving average filter. Another issue with filters is that they can introduce lag or phase shifts in the signal. Now, this is shown on the left, where the original signal is in the blue and the smooth or average, the moving average signal is given by the red signal. When you can't see the future or the entire signal, then you usually need more sophisticated methods to mitigate this lag. However, if you're working with the entire time series in an offline manner, then you can simply apply what is called a centered smoother, which uses both the past and future values to smooth the data at a point. In general, this mitigates some of the lag. Another useful technique from signal processing is for finding edges in a signal that only has the values of 0 and 1. And we do this by applying what's called first-order differencing. First-order differencing is the discrete time analogy of the first derivative you might have learned about in your calculus class. For a discrete time series, the first-order difference is actually even simpler than the derivative. It's just the change of the series at a given point in time. For a binary valued signal or a 0-1 valued signal, a first order difference that equals 1 corresponds to the starting edge of a rectangular block. So here we have a series of rectangular blocks in black. And when the first difference is 1, this corresponds to an up edge in the signal for that block. While a first order difference of -1 corresponds to the end of the signal. So we can see here by green, by this green signal. So you can create, based on this first order differences, you can create routines to identify the start and edge of every rectangular block in such a signal. So now on to the feature engineering for this model. Here's the basic process for identifying the various blocks in time when they're either pumping acid or proppant. First, we smooth the signal with a short-centered median smoother. We choose the smoother again to try to get rid of the high frequency fluctuations, which we typically attribute to sensor noise, while trying to maintain edges as much as possible. Next, we normalize the proppant concentration signal to lie between 0 and 1. This normalization effectively removes any dependence on units or even any job or formation related concentrations. Value changes are now simply expressed as percent changes. If you watch a subject matter expert label the start and end of these proppant concentration values, you'll see that they don't actually pay close attention to the values themselves. Instead, they're looking at behavior. And by behavior, I mean sustained increases from 0 concentration to a non-zero concentration for a block of time, and then decreases from that sustained concentration back to zero to find the start and end of each ramp. And that's what we're trying to do. So next, the model will round or quantize the values in the prop and concentration channel into a fixed number of buckets. So again, we're trying to get rid of noise, and this is almost like pixelating the data. Like if you've ever seen a low quality image, that's kind of what we're trying to do. Because again, at this stage, we're looking only to find the start and end of each block. The precise values don't matter. So next, the procedure will create a binary valued signal where the signal is equal to 1 precisely when this pixelated or quantized prop and concentration is greater than 0, and otherwise the block is 0 otherwise. So like in this example, you'll see that these 1s correspond to where you see prop and concentration being pumped. Now, unfortunately, this plot is a little bit idealistic because the signal, this block 1 at the very end, which I call the event signal, should be 1 precisely during acid pulses and proppant ramps. But because the data is noisy, this doesn't happen all the time. The first step in converting the event signal closer to its ideal form is to apply a centered median filter with a longer window to this last channel at the end, so this rectangular block 1. This has the effect of removing some of the short islands and gaps in the event signal that might occur during the middle of a proppant ramp. This smoothing step could be removed by augmenting the next step that I described below. Oh, before I get to that, just a quick note for those of you using median filters on 0-1 signals. Using a rolling or moving median filter with a window length that is an odd number ensures that a 0-1 valued signal remains a 0-1 valued signal after applying the filter. So the next step is to split the binary valued signal into different proppant blocks using the first order differencing technique from a couple of slides ago. Now for each proppant block detected, the model computes the duration of the block and the total clean or slurry volume pumped during that block. This helps us identify the difference between the acid and a longer proppant ramp. The model then uses simple operating rules to identify which blocks realistically correspond to proppant ramps. For example, the model can remove blocks that are too short, where the threshold for too short can be learned or calibrated from the data. Now, you can use a more ambitious identification procedure that tries to quantify the shape, but we found that the simple duration rule is good enough in practice. Additionally, small blocks that are close to large blocks can easily be merged together depending on the preferences of the business. Now, in order to discuss how we find the proppant steps in each proppant block, I want to discuss decision tree regression or recursive partitioning. Now, this is a well-known statistical technique to identify functional relationships that aren't necessarily linear. Decision trees are the building block of the extremely popular and versatile random forest technique used in many machine learning tasks. A less well-known application of recursive partitioning or decision tree regression is to fit piecewise constant curves, similar to how a linear regression can be used to fit a straight line relationship. Now, most of the time when people talk about decision trees, you see the associated tree or flowchart diagram. So here's a plot where I compare linear regression to decision tree regression, where I represent both as graphs of functions. So here the red line is a linear regression fit through the data. The blue segments are actually the output of a decision tree regression. Most people who've worked with decision trees haven't seen how the function fits in a 1D prediction, because usually we resort to decision trees when we have multiple variables, predictor variables, and so it's easier to visualize it, the model, in terms of its flowchart. When you're using one predictor variable, like we are, this is actually a useful insight as to what a decision tree regression is doing. So the problem for finding the Proppen steps is a textbook application of recursive partitioning or decision trees, since if you look at the plot, the Proppen ramps that are pumped in steps are effectively piecewise constant. Now, for the case of fitting Proppen concentration versus time, we can look at the resulting decision tree flowchart diagram. This is the common way of looking at it. In this flowchart, the final nodes, that is nodes without any arrows leaving, represent segments of time with approximately the same Proppen concentration. Now, if the fit is perfect, then each final node will capture time segments with the same target information. The nodes, the rules for the nodes in the middle of the decision tree are going to have the general form: if the time is earlier than this, then go left, otherwise go right. Using these models and that final post-processing modeling step, we can fully describe the pumping schedule. So our data set used for training, validation, and testing was pulled from various jobs, service companies, and operators from all over North America over a period of several years. Actually, before I go into the data set, I want to give you an example of what the deliverable for this set of models looks like. So on the left, you'll see the treatment plot. We applied the machine learning models, and the output is what you might find in a PDF document describing a fracture treatment pump schedule. Notice we identified the acid pad, the pad, and the various Proppen step concentrations, followed by the flush. So while we didn't do any sophisticated, fancy deep learning, we just effectively applied some simple machine learning ideas well to generate an automatic workflow for a process that's extraordinarily tedious and error-prone and extremely time-consuming. Now, let me talk about the accuracy. The accuracy of the entire process on our test data, so the data that the model has never seen before, will be broken down into two steps. First, the process was able to recognize about 96% of the labeled flags overall. That is, it failed to report an event about 4% of the time. There were no cases of a spurious event being predicted. The second step of the accuracy describes the error on the treatment events that it was successful at recognizing. A standard way to report this type of accuracy is to list percentiles of the time difference between the manual and predicted flags. So in this case, for this model, 95% of the predictions were within 3 seconds of the manual pick, while 97.5% of the predictions were within 1 minute of the manual pick. And so just because this process might seem complex, we've successfully applied simple ideas to produce a huge improvement in the workflow and the speed at which these types of schedule generation process can be done. And so that concludes the main part of my presentation. I'd like to thank you for your attention, and I look forward to your questions. I do have some extra slides on deep learning, some hard lessons that I've learned over the years, as well as how my team at Well Data Labs does their modeling process if you're interested. Otherwise, we can just take questions from the audience. Thank you.
All right, thanks, Sam, for that. Let's see. Right now, we'll go ahead and go into the question and answer portion of it. If you'd like to continue, just go ahead and mention that, please. You can either raise your hand or go ahead and type in a question, and I'll wait a few moments for any of that to begin. start going through the last few slides that you have there, please?
Sure. So let me first talk to you about some of the mistakes, some of the lessons I've learned from doing this for several years. So in principle, like what I'm going to describe are like 3 rules that I use for mathematical modeling. And this includes work in optimization, statistics, machine learning, and even AI. So the first rule is that models aren't real. I love math, but math is neither truth nor authority. It's just a lens to view the world. All too often, I see people trying to change reality to fit their models instead of changing their models to fit reality. And when you're doing machine learning, you're engaging in mathematics, whether you realize it or not. The second rule is be a skeptic. I have this quote by Richard Feynman, is like the first principle is that you mustn't fool yourself and that you are the easiest person to fool. It's important that you understand your model's assumptions, you understand your method's assumptions, and that you understand your algorithm's assumptions, because all of them have assumptions baked in. And that's sort of the problem, one of the problems I have with these flowchart recipe type approaches to applying methods. And the third one goes out to people who are math experts or machine learning experts. If you're fluent, don't be a snob. I say that somewhat tongue-in-cheek, but you know, I've had the privilege to work with some of the top researchers in the world back in grad school, and one notable characteristic that they all shared was their willingness to discuss ideas and engage in debate, even with a first-year grad student. And for them, that's a lot of effort potentially, because it meant that they had to come up with creative ways of helping me build intuition into complex or novel ideas. And unfortunately, I've seen my experiences in industry haven't lined up quite as often with that. Just remember that your colleagues might not be as fluent, and that the goal, one of the things about being an effective and pleasant teammate to work with is to remember you want to have transparent and constructive conversation. Shutting down conversation by pulling out mathematical sophistication is extremely counterproductive and honestly makes you just overall less effective at your job. Another thing that I wanted to talk about is sort of our team's model development process. We've generated easily over a dozen practical workflows in the last 2 years, and part of our process is what I would attribute to this success. One common misconception is that a model, especially a machine learning or a deep learning model, needs to solve the target business problem all at once. This type of development process tends to produce overly complicated models with long review and project evaluation cycles. It's important for data scientists in industry to focus on adding business value and avoid the temptation to solve complex problems with the newest and most cutting-edge methods. Many problems, as I've said before, rarely require sophisticated methods to produce good results. Our team has been really successful at applying a lean methodology approach, where the best practice is to break down problems into very small tasks and rapidly iterate on them. The aim is to build minimum viable products quickly. I'll list out 4 advantages off the top of my head. 1, you're able to quickly identify bad or missing data. 2, you're able to quickly identify misconceptions about the data and the data generating process. 3, you're able to take advantage of partial automation quickly when you are successful. And 4 is failing fast. This 4th point is especially salient for company resource allocation. If your team cannot solve a simple part of the problem, then why would you waste resources on solving the more ambitious problem? Instead of trying to build a model that recognizes all the relevant events in a pumping schedule at once, our team decided to split the problem into recognizing each of the major steps and then combine the separate steps to produce the final result. And this can even extend to the types of data that you work with. So for us, oftentimes we start off with the clean textbook examples during our model development process. And the reason for that is if we can't develop a model on even these textbook cases, we're going to have very little hope of developing a model for the most difficult cases in that we'll see in practice. I'm going to leave out the slide on deep learning because I don't want to be any more controversial than perhaps I've been during this talk. So again, thank you for your attention. I'm more than happy to take questions. You can feel free to email them. I have my email address listed on this final slide. And with that, I'll turn it back over to Anthony or Ronnie.
Okay, thanks, Sam. Yeah, we do have a few questions now. The first one says, thank you for the informative presentation. I probably missed it, but for the binary data smoothing, did you say you use a median filter?
I do use a median filter, and there's just a one caveat with using a median filter with a 0-1 valued signal, is that if you want the signal to remain 0-1 valued after the smoothing, you need to use an odd-sized window. And the reason is, if you remember the technical definition of a median, if you have an even number of things that you're taking the median of, you take the average of the middle two. And in this case, it would produce 0, 1, and a 1/2 valued signal. So if you want to keep the signal 0-1 valued after the smoothing, you should use an odd-sized window.
Oh, okay, thanks for that. Are there any open source data available if you want to try ML on well data?
Oh, you could reach out to our customer success team. So if you go to our site, there should be a contact me link, and we have people that can talk to you through several of our models. We've got, I believe, at least a dozen either deployed directly inside the app or that are in the process of being deployed to the app. We call them power-ups, and you can take your hydraulic fracturing treatment data, and you can click this robot button that we have, and it will do these event identification as well as generating some of these summary statistics for you. This is an active area of development for us right now at Well Data Labs. If you're interested in joint projects for doing machine learning or AI, our research team, of which I'm a part of, is always looking for interesting opportunities to work with our customers. So, you can feel free to reach out to my email address, and I can either direct you to the right person, or you can go to our site and we have some good contact information listed there.
Awesome, thanks, Sam. Also, we do have their site that we sent out on the invitation, a link to it. Plus, you can find it on our social media, just to let you know. Next question. The machine learning model created by you related to hydraulic fracturing can be applied to other data sets. Is that true? Or can it just be applied in that particular case study?
Oh, it can be, as long as you're looking for prop and steps, like if you're looking for generating the schedule, this will take anybody's frac treatment, it will take anybody's treatment plot and generate the frac schedule like you see here. It's not for this one particular stage. We tested this across hundreds of stages from various jobs, from various operators, from various service companies across different basins over a period of years. So the step procedure, you need to have the job needs to be pumped in steps for the step procedure to work. If they've pumped it using a continuous ramp, since you're not going to have steps, it's not going to detect steps, but it will still be able to to flag the acid pulse at the beginning, and it'll still be able to identify the start and end of various propant blocks, give you the duration and any other summary statistics that you're interested in. Hopefully I answered your question. It's a general thing, but it needs to be for this treatment, for this hydraulic fracturing treatment data.
Here that has their hand up. Edelson Domingos, I'll go ahead and unmute you if you'd like to go ahead and ask your question, please. Oh, there it goes. Okay.
So my question has to do with this same page here with the pumping schedule and the model that was created for this using artificial intelligence. I'm still trying to put together the pieces as far as what artificial intelligence can actually do, for like designing, fracking operation. And my question is, how did artificial intelligence come into role for this specific example here? Did you generate this pumping schedule using artificial intelligence, maybe based on a database of previous jobs for similar situations that you already had, or is it more something in the sense that engineers design the pumping schedule and then you're using artificial intelligence to try to determine how close to the design reality is actually going to be? Like, can you elaborate a little bit on that? Can you clarify a little bit on that, please? And thank you in advance.
Oh, absolutely. And I guess maybe in my rush to describe it, I didn't sort of explain the motivation well. So the idea behind this this model is to be able to analyze a historic frac treatment job. So a job that has been previously pumped. And, to be able, this could actually be different from the designed treatment. So, you might design a treatment with certain assumptions in mind, but once you start fracking the job itself, you might have unexpected pressures. You might find that the job is treating tighter than you expected it. So there are going to be deviations from the job that's actually pumped from the design job. So the idea is, well, how do I compare the two? So what this method does is that given a historic treatment, it reverse engineers the actual pumping steps, so that now you can take the pumping steps, you can take the steps that were actually pumped and compare it. One workflow is to compare it to the actual designed job and see how they differ. Moreover, you can take the as designed schedule and use that in your fracture simulator and potentially play with other knobs to maybe like change stresses or things like that aren't that are part of the fracture simulation to better line up. It's sort of like akin to, like, it's not exactly like history matching, but it's taking like the actual data to help you better inform a theoretical simulation. So there are multiple workflows that you can spawn from this. So again, it's not to predict a pumping schedule. The idea is to take a historic pumping schedule and reverse engineer the schedule that was actually pumped, instead of having an engineer go in manually and label, here's the acid, this is how much acid was pumped, here are the different proppant blocks, here are the concentrations. Like, that takes time to go in and label it yourself. This takes, I believe, for most jobs, like less than a second to actually label an entire stage, and maybe a couple of dozen seconds isn't. I'm being pessimistic about it. A few seconds for an entire job with all the stages to be reverse engineered. So this is a huge improvement in efficiency. Doing this by hand, I know it sounds like I'm potentially exaggerating, but for a single well with 40 stages, this could, in principle, take an entire day's worth of work. So reducing it to a minute or two is a huge improvement in terms of efficiency. Plus, nobody likes labeling data. I mean, wouldn't you rather like just take the output and actually work on the Frac simulation rather than going in and actually labeling the data? I mean, I know that most people don't like labeling data, so, you know, kind of tongue in cheek, like it also avoids like a tedious and boring workflow.
All right, thanks, Sam. I'll go on to the next written question. Let's see. In all these applications you've mentioned, do you know the average accuracy?
Yeah, so that was the slide that I talked about. Like on this slide, I talked about the accuracy at the end. And so there are two ways to quantify it. So like the first way is how many of these events were successfully recognized. And I mentioned that for this particular workflow, that 96% of the events were successfully labeled, and we didn't generate any spurious events. And then for the events that it did recognize, 95% of the predictions were within 3 seconds of what a subject matter expert would pick. And then the 97.5% of the predictions were within 1 minute. Some of the cases, so you notice that at the very end, like there are some genuinely difficult cases that the model does have trouble with. But because the 95% of the cases are labeled so well, this is a huge improvement in the workflow. Remember, it's a false dichotomy to say that a machine learning model has to be perfect before it's deployed. You know, if you're able to automate over 90% of a tedious and time-consuming workflow, that gives you a 10x speed up in terms of how quickly you're able to speed up it gives you a 10x improvement in how fast you're able to label all of this data. That's nothing to sneeze at. So you're already getting a huge improvement. And moreover, the labeling will be consistent, which again, like if you remember some of the earlier slides, consistency is actually a big deal. And because this is an automated procedure, its picks will be much more consistent than having several engineers going in and labeling these events by themselves.
Okay.
Hopefully that answers your question.
It seems like it. If you feel like you need to do a follow-up question also, please just go ahead and either post it or raise your hand and we can do that. The next question, I think I skipped one, but I'll go back to it. Any thoughts on adding Fourier series components into your example?
So one answer is when you're doing filter design and selection, in a way, you're kind of doing a Fourier series analysis anyway. Because we do signal processing and I really enjoy it, there are opportunities for doing like a Fourier series decomposition of various things, and you can just add them in as auxiliary features for a machine learning model. And I've had a little bit of success with it, but I guess the point to remember is that Fourier series, especially for time series data, is especially helpful when you have periodic data. So things need to look like waves. In a lot of the hydraulic fracturing treatment data, you don't often see that. You might see it when you zoom into the data because of the sensor noise. And like the usual narrative that people in filter design like to work with is that the noisy part, especially in sensor data, can be viewed as high frequency data. And so when you're designing a filter, you can do Fourier inspired analysis to make sure that you are getting rid of the noise that we like to tell ourselves is coming from sensor noise. But aside from the water hammer, I haven't really seen a lot of wave-like effect or phenomena in hydraulic fracturing treatment plots. So I love Fourier series, but I haven't really found, aside from the water hammer, an opportunity to really apply it in its kind of full glory for this type of work.
Okay, thanks for that answer. Let's see. Hey, Sam, could you talk about some of the test data your initial algorithms failed on? Why and how did you fix them?
Ah, okay. That's a really good question. So, the examples that I have in these slides are showing really clean treatment plots. If you look at treatment, if you look at lots of treatment plots like we do at Well Data Labs, you'll see a lot of trouble stages that either treated tight or have various concerning pressure responses that involve either cutting rate or adding friction reducer. So while this plot on the left is showing like a very clean stage, oftentimes like stages won't look like this. And sometimes they'll cut sand in the middle of a job if there's a concerning pressure spike. So when I mentioned here about merging or removing blocks, these types of refinement steps arose to deal mainly with, okay, so we're having a hard time following through on the design, and we're cutting rate. We might cut sand, and so this can create gaps in the proppant concentration signal, or sometimes we even have sensors go down and they're not switched. It takes them a little while to switch to the backup sensor in the data, and so again we have gaps in it. So this simple logic around merging and removing blocks was a lot of the motivation for that came from dealing with like the difficulties in dealing with real data, like the messy non-textbook stages. So for example, here in this model iteration slide, I took this slide from my colleague Jess, and she was talking about placing flags for the start and the end of the stage. And so the very top example is a really clean stage. It has a very clearly identified proppant or pressure test, and it has just a minimum bit of the fall off. But if you look at the very bottom example where the 95% is, like there are multiple pressure spikes in the beginning, there are multiple pressure tests. They actually, you can see a little bit of fluid being pumped and then the pumps being shut down. Those are the reality. But again, part of the reason for this model iteration process that we've developed is like, if you can't develop a machine learning model for that 60% example on the top, then why are you going to waste resources and staff and effort on trying to solve the 95% case, like the case that's really difficult? So again, from a stewardship, not exactly a stewardship, but from a resource allocation standpoint, it's really important that you make sure that you're successful in the textbook cases before you go on to the real world cases, because a hydraulic fracturing treatment can be extraordinarily complex in the field when things don't go according to plan.
All right, thank you, Sam. We have somebody that has their hand raised. Kildare George, go ahead and unmute you right quick if you'd like to go ahead and ask your questions.
Yes, can you hear me?
Yes, we can hear you.
Yes, so I am Kildare George. I am a PhD student at Texas A&M. So I have just one question. I mean, it's more like a clarification, right? So for each pumping schedule that you have, you need to create a model, right? Is that right?
We have one generic model that you feed the pumping schedule. You feed a generic pumping schedule in, or I'm sorry, we have one model that you give it a stage of hydraulic fracturing data with the proppant concentration, the slurry rate, and the treating pressure, and it'll spit out a pumping schedule in like the table you see on the right, based on that. So we don't do multiple models. Like we've already trained and built a generic model for this.
Okay. Okay. So for example, in this case that you have presented, how many examples you have used to train your model?
Okay, that's a great question. So we used several hundred. If I'm trying to remember correctly, I'm not going to get the exact numbers right. I don't have them handy. There were between 500 and 600 stages that were, and this is the catch, they were from all over North America, so all the major basins, from multiple service companies, from multiple operators over a period of years. I think it was 5 or 6 years. So we covered a gamut. We had a wide variety of pumping schedules that we used for training or calibration.
Okay, now it makes sense. Okay, so that's why you have applied your model in many cases, and pretty much in all of them, it resulted in good accuracy at the end, right? So you had like you had like a really good training set. Okay. Okay. Thank you very much for the clarification.
No, I mean, and thank you for the question. I apologize that it wasn't clearer as I was talking about it.
Okay, thank you for that. Let's see. Another question, how much input data was required to get these results? For example, how many total frac jobs were considered? I think it's very similar to the question asked earlier.
Right, and that, like I said, I'm almost positive off the top of my head that it was at least 500 or 600 stages. And the important thing is that they weren't all the same type of stage. Like they included stages like the ones you see here with 90% and the 95%, where there were multiple proppant blocks that were being pumped. So like it wasn't just this textbook stage that I have for the sake of illustration here. If I included a more difficult job, the pumping schedule would be really difficult to fit on a slide.
Okay, and it looks like a couple of more questions. Say there you have somebody that is wanting to go down the road of learning the data analytics and data science. Do you have a good place to start learning, like some resources or anything like that you'd recommend?
Yeah, I think, so one of the things that I joke around about with my data science colleagues is that data scientist as a title might actually disappear in a few years. Because I feel like with the access of all these really convenient libraries and tools, it's just going to be expected that the next generation of engineers and scientists that come on are just going to have better skills. Like for me, I remember hearing from some of my slightly older colleagues that this was very akin to the transition to using Excel from just doing everything on graph paper and yeah, like starting to use spreadsheets. Like we joke about it now, but every engineer and scientist knows how to use Microsoft Excel. I think what we're going to see in the next 10 years or so is something very akin to that in terms of using data visualization tools such as Spotfire or Tableau or Power BI, combined with some basic programming skills aside from VBA, so some basic Python or R. And so I don't have the list of resources off the top of my head right now, but I've mentored several people over a number of years, and I've gone through a bunch of these online courses. There are some good courses on Coursera. There are some good courses on Udacity that can be really helpful. And the reason I like some of these online resources, and as opposed to textbooks is there's a component to these online courses where you have to do exercises. You cannot, like, statistics and machine learning is, as I mentioned, is an applied field, which means that you really can't learn it out of a textbook. You can get ideas out of it, you can build foundations for how to think of it, but if you're not doing it, if you're not doing data analysis all the time, you're really not applying that theoretical knowledge, and that theoretical knowledge isn't all that helpful. So again, remember, like, ML is very, like, machine learning and stats are very, very applied. So what I recommend to a lot of the people that I mentor is take something. It can either be a work project or it can be something at home. I had one of my mentees do something with Spotify playlists. As long as you're interested in it, and then, like, keep hammering on that data set using the different techniques that you learn so that you understand the pros and cons of various things. It's really, this applied component is really important. And for those of you who are working, I get it. You know, like, working 8 or 9 to 5 or even longer than that every day, you have very little energy outside of work to go and learn another thing. That's why I recommend for these, like, applied projects, do it on something you love. Like, it can be about fishing, it can be hunting, it can be COVID if you're so interested. Make sure that it's something that you're engaged with, because again, you can read about this stuff as much as you want. It really doesn't stick well, and you don't really appreciate the nuance until you get your hands dirty. I know I didn't really directly answer your question. Feel free to use my to reach out to me at my email address, and I'm more than happy to work with you in terms of, you know, talking about online courses or even textbooks, because that depends honestly on your background and where you're starting from.
Okay, well, great. Thank you for all that, Sam. We appreciate your time with us. We thank you for the great presentation and answering all of our questions. Once again, for those of you that have attended, we will email out and let you know when the recording will be available, and we'll also be putting that out on our social media as well. Thanks everybody for attending. Thank you, Sam, and we really appreciate the great presentation.
Thank you, everybody.
Thanks for your time, Sam. Appreciate it.